Greetings everyone, and welcome back to our next lecture in our online lecture series for CHE 2300. In today's lecture, we are going to extend last video's lecture to talking about convective heat transfer for pipe flow. So from last video, we saw that H, our convective heat transfer coefficient, depends on both the Reynolds number and the Prandtl number. Let's see if I can get this right. The Reynolds number and the Prandtl number. In what I don't think I actually used the term in the last video, we call forced convection. So what do I mean by forced convection? Forced convection simply means that an external force is applied to drive fluid flow. Right, simply meaning that we are, pumping our fluid through a heat exchanger. That would be an example of forced convection. We will talk about the other type of convection, natural convection, in our next video. So in the last lecture, we saw that convective heat transfer coefficient H depended on the Reynolds number and the Prandtl number for flow over our flat heated plate. And one thing I did point out in the email that I'm going to point out again here, we had our Nusselt number equal to our convective heat transfer coefficient. And let's go ahead and assume pipe flow, the diameter of our pipe, and then the thermal conductivity. This is the thermal conductivity of the fluid. And the same goes for the Prandtl number. Our Prandtl number was equal to the specific heat multiplied by the viscosity divided by the thermal conductivity. All of these are for the fluid. Okay. So along with the Reynolds number, along with the Prandtl number, there are a couple of other important dimensionless numbers that I want to point out. The first of these is the Graz number. I'll abbreviate that with GZ, and that is equal to the mass flow rate of my fluid multiplied by the specific heat divided by the thermal conductivity of my fluid multiplied by some length. And the Graz number is traditionally more important when we're discussing laminar flow. And it is a ratio of the time for radial heat conduction into a fluid divided by the time taken for that fluid to reach some length. Right? And this is typically thought of in terms of an entrance length to a pipe. So I am pumping a fluid into a heated pipe, and the fluid enters that pipe at some temperature. It's different from the pipe, and over what length scale does my temperature boundary layer develop? Right? This is what my Graz number is going to be able to tell me. I know based on the cross-sectional area and some of the properties of the fluid how to calculate my mass flow rate. If I plug that into my dimensionless number here, let's draw that correctly. I get the following equation, and it may not be obvious, so I'm going to rearrange that equation a bit. So GZ equals pi over 4. The first grouping I'm going to pull out is rho V bar D divided by mu. Oh, excuse me, sorry. This is going to be confusing if I don't indicate what I'm doing here. So let's erase this. Let's go back up to our equation. What I'm doing here is I'm going to multiply both sides by a ratio of my viscosity. So that's going to go away, and then I'm going to group my viscosities accordingly. So I have pi over 4 rho V bar D divided by my viscosity. And then my next grouping is going to be Cp, my specific heat, viscosity, divided by the thermal conductivity. And then that leaves me a D divided by an L. Hopefully we recognize those two ratios in the parentheses. And we end up with pi over 4 times the Reynolds number times the Prandtl number multiplied by that ratio of the diameter of our pipe and the length of our pipe. Okay. Another parameter that you might run into when discussing heat transfer in fluid flow is the Peclet number. So the Peclet number and the Peclet number is equal to, let me give myself some space here. The Peclet number is equal to the Reynolds number multiplied by the Prandtl number. So dV bar rho mu Cp mu divided by K, which I can rearrange in the following form. Where this variable is my thermal diffusivity. Diffusivity, and is equal to the thermal conductivity divided by the product of the density and the specific heat. So the Peclet number is a ratio of convective, so there's my convective term, my velocity, to diffusive, where I have my thermal diffusivity, heat transfer. So we have the Graz number, which gives me an idea of radial heat transfer into my fluid, divided by the time it takes for that fluid to reach some length into my piping system, let's say. We have our Reynolds number and our Prandtl number. We know what those are from our last lecture, and hopefully we know what the Reynolds number is from the first lecture of the course. Our next dimensionless number, well, let's not forget our Nusselt number here, which is a ratio of convective to conductive heat transfer. This is conductive heat transfer within the liquid or fluid near the boundary. And now we have the Peclet number, which is a ratio of convective to diffusive heat transfer. We can relate, let's pick another color. We can relate the Reynolds number, the Prandtl number, and the Nusselt number through an additional dimensionless number known as the Stanton number. And this is equal to the Nusselt number divided by the Reynolds number, or the product of the Reynolds number and the Prandtl number. And this equals our convective heat transfer coefficient divided by our specific heat and multiplied by our mass flux or our mass velocity. This number, the Stanton number, is a ratio of heat transferred into the fluid to the thermal capacity of the fluid. So a ratio of heat transferred into the fluid, right, this is given by our convective heat transfer coefficient, to the thermal capacity of the fluid, which is given by our specific heat, which gives us an idea of how much energy we need to raise some mass of our fluid a degree Kelvin, or excuse me, a degree Fahrenheit or degree Celsius. Okay, so let's consider a fluid that is flowing through a pipe where the pipe wall is held at a constant temperature T sub W. If we have the case of laminar flow and our Graz number is greater than 20, then the Nusselt number can be approximated as 2.0 times the Graz number to the 1/3, or 1.85 multiplied by the Reynolds number, the Prandtl number, and our ratio of the diameter of our pipe and length of pipe, all of that raised to the 1/3 power. Here, our Reynolds number and our Prandtl number have a subscript B, which represents what we're going to call the bulk. And what I mean by that is that here I have my fluid. It is flowing through a wall. The wall is being held at a temperature T sub W. That doesn't necessarily mean that that wall temperature or the entrance temperature of my fluid is the best representation for the average temperature over the entire length of pipe. And so what you'll see down at the bottom of this page here, and I'll go ahead and jump down here, is that all of our parameters, Reynolds number, Prandtl number, and the viscosity, and we'll see in a second what I mean by this, are evaluated at the mean bulk temperature, where our mean bulk temperature, T sub B, is equal to the temperature of our fluid entering the pipe. So, entrance temp, and the temperature of our fluid exiting the pipe, divided by 2. So simply the arithmetic mean of the entrance temperature and the exit temperature of our fluid. That is what we're going to call our mean bulk temperature, and we're going to use that temperature to evaluate our Reynolds number and our Prandtl number, and also what we're going to call our bulk viscosity. It says for very viscous fluids, let's say for, I don't like how I wrote that, for fluids, let's say for high viscosity fluids. We need to add a correction term to the above equation to account for the fact that there are differences in the velocity profile whether we are heating or cooling that viscous liquid, meaning that, the temperature profile, right? And that's based on the fact that near the wall, depending on whether we're heating or cooling, we have a different viscosity of our fluid than we do from the bulk viscosity of the fluid that is moving in our pipe. So we need to account for that. And so we can introduce a correction factor. And our correction factor is equal to the ratio of the viscosity of our bulk fluid, the viscosity at our bulk mean temperature, divided by the viscosity at the wall temperature. And all of that raised to the 0.14 power. And so this exponential here already indicates that this is some type of empirical correction factor, meaning that there is some data collected. They saw there was a discrepancy in the model and the data, and they realized that they needed a correction factor to account for these differences for highly viscous fluids. We can take that correction factor in equation 4, add it to equation 3, and we have our final equation here that tells us the Nusselt number is equal to the convective heat transfer coefficient. And here, here I'm going to go ahead and define this as H sub I, meaning the convective heat transfer coefficient on the inside of the pipe. That is going to be based on the inside diameter of the pipe divided by the thermal conductivity of the fluid that is moving through the pipe. And all of that is equal to 1.85 multiplied by the bulk Reynolds number, the bulk Prandtl number, our ratio of the diameter of the pipe and the length of the pipe, all of that raised to the 1/3, and then we add our correction factor here onto the end of our equation. If we have a low viscosity fluid, meaning if we have something like water that's moving through our pipe, then the viscosity of the water at the wall and the viscosity at our bulk mean temperature should be similar, and our correction factor becomes 1. Again, our correction factor we have when we have flow of high viscosity fluids. Okay, before we continue on, I did want to point out, if we go back up here to our Graz number, that sometimes you may see, and I meant to do that after we define the Peclet number, but sometimes you will see this written as D over L times the Peclet number. So D over L times the Reynolds number and the Prandtl number. Meaning sometimes you will see it without this pi/4 factor. So for the textbook that we use and everything that we'll be doing, it will include that pi/4 factor, but just be aware that if you use a different textbook, they may define the Graz number a bit differently than McCabe, Smith, and Harriet does. Okay, I said all this, but I'm going to go ahead and go over it again to make sure that it's clear to everyone. When I write here the viscosity SubW, I'm talking about the viscosity evaluated at the wall temperature. Right, so let's say that we have something like we have a highly viscous oil that comes into a heated pipe, and the oil comes into the pipe at 20 degrees C, and the pipe is being held at 150 degrees C. Right? We would need to calculate the viscosity at the 150 degree C temperature of the wall, as well as calculate the viscosity of our oil at the bulk temperature. And so let's say it enters at 20 and leaves at 70 degrees C. We would take that and we would add those two together, divide by 2, and we get a bulk temperature of 45 degrees C, which we would use to evaluate the bulk viscosity of our fluid and use that to calculate our correction factor here to account for or to correct our Nusselt number equation for the high viscosity of the oil. Second bullet point says that all other parameters, that includes our bulk Reynolds number, our bulk Prandtl number, and again I just use the example of our bulk viscosity, are evaluated at this mean bulk temperature, which I'll point out one more time, is equal to the arithmetic average of the entrance temperature and the exit temperature of our fluid. So up to this point, right, the equations we have been discussing have been for laminar flow. What about turbulent flow? For turbulent flow, we can define a slightly different equation. So we have our Nusselt number equal to the inside convective heat transfer coefficient multiplied by the inside diameter of my pipe divided by the thermal conductivity of my fluid is equal to 0.023, my bulk Reynolds number to the 0.8 power, my Prandtl number, my bulk Prandtl number to the 1/3 power, and then that multiplied by my correction factor. This equation, if we box it in, that'll help, is known as the Cedar-Tate equation. There is another equation out there known as the Dietz-Boelter equation. That is simply this equation without the correction factor. We add the correction factor, it becomes the Cedar-Tate equation. A couple restrictions for the use of this equation. The first is that we have bulk Reynolds numbers greater than 6,000. The equation works reasonably well for all turbulent flow, but works best if we're talking about bulk Reynolds numbers that are greater than around 6,000. And this should not be used for molten salts. Okay, so we have our equation for laminar flow. We have our equation for turbulent flow. And one thing I'm going to stop here and take a second to point out, although hopefully it is obvious, but our Nusselt number, which contains our convective heat transfer coefficient, is a function of the Reynolds number, meaning it is a function of the velocity of the fluid. Right? Better heat transfer occurs in the turbulent regime, therefore the majority of heat transfer equipment that you will run into out in industry will be operated when the fluid is in that turbulent regime. That is because my convective heat transfer coefficient, I want that to be as high as possible. A high value of the convective heat transfer coefficient indicates good convective heat transfer. That is a direct function of the velocity of that fluid. Okay. Laminar, turbulent. Now what about if we are in that transition region. If we are in the transition region, we use what we call a Coburn J factor, and it's derived through an analogy of skin friction and pipe flow. The J factor, see if I can fit all of this in here. I'm not even going to try, so I'm going to start outside my box. The convective heat transfer coefficient on the inside of my pipe divided by the mass flux or mass velocity multiplied by the specific heat. That is multiplied by my Prandtl number, which I'm going to write out. Let's say K to the 2/3, my correction factor. Let's just write it out because it's actually 1 over the correction factor in this case. So in this case, it's the viscosity at the wall divided by the viscosity at the bulk to the 1.4 power. That is equal to my Coburn. That is equal to my Coburn J factor, which is also equal to 1.86 D over L to the 1/3, and D times my mass flux divided by my viscosity to the negative 2/3. Okay? So this is my equation that I would use if I had flow in the transition region. That equation right there is plotted on the following page for various values of L over D. In this case, we have two values. L over D equals 50, L over D equals 100. And so how would I use this particular chart here? Well, in this case, the first thing I would do, which I'm going to typically do with most of my problems, is to calculate a Reynolds number. A bulk Reynolds number in this case, because my viscosity is going to be evaluated at my bulk temperature. Then let's say in this case I'm going to assume that my L over D is equal to 50, and that my let's say that my Reynolds number is equal to bulk Reynolds number equal to 2,000. No, because that's still laminar. Let's say 33,000. Let's make it easy on ourselves. So 1,000, 2,000, 3,000. I calculated my Reynolds number. I know I have an L over D of 50. So I follow this up to my curve. So find my Coburn J factor from plot. And then knowing what my J factor is, I can calculate my convective heat transfer coefficient on the inside of my pipe. So calculate HI knowing this J factor. Okay, so hopefully that makes sense, but that's how I would use this Coburn J factor to calculate a convective heat transfer coefficient when I am in this transition region. Alrighty, so that ends our lecture today on convective heat transfer in pipes. I will also be uploading a video very shortly where I work through a couple example problems for forced convection to help you better understand and appreciate when and how to apply these equations and what type of problems you might run into on, let's say, homework or an exam, something like that. So please be on the lookout for a video where I am solving at least 2, maybe 3 example problems involving forced convection.